All right, hello again, everybody. I just wanted to make a short video following up on the R commands video I made yesterday, where we walked through this set of commands, talking about normal distributions, how to generate them, and how to plot them, so on and so forth. I'm going down to the second part of this little web page here, talking about transformations, which is something I lectured about in reality a while ago, but hopefully you watched that video not too long ago, so you still remember pretty much everything I said. And so in the transformations video, we talked at some length, or I talked at some length, sorry, about converting between Celsius and Fahrenheit temperatures. So for that reason, I'm going to load up the weather data again. And again, it takes a while because there's a lot of data in it. We'll just take a look at how to make that sort of conversion in R. It's pretty straightforward. I'm going to use this attach command, which I mentioned in one of my previous videos on R commands. Not going to make that much use of it, but remember, it's useful if you do throw it in there when you load up a data frame. And then the first thing I'm going to do, if you remember, a command that is also useful on top of the attach command is the summary command to find out what we're looking at. Just to remind you, these are the sort of high and low temperatures and average mean temperatures for each day in the year for Calgary and Toronto, going way back when. For Calgary, basically to the foundation of the city in 1881. And what I want to do is just take a look at the Calgary highs. So the high temperatures in Calgary, these are listed in Celsius for what it's worth. So like the max temperature at this point in history was 38 degrees, which would be really bad for Fahrenheit, but it's pretty hot for Celsius for a high temperature. I think maybe somewhere in Antarctica, the all-time high has been 38 Fahrenheit. But otherwise, it's pretty cool Fahrenheit, pretty hot Celsius. We're going to take those high temperatures and dump them into this vector called Calgary highs. So when I take a look at the summary of that information, what we're doing here is just looking at the city of Calgary by itself. I get a different sort of distribution. This gives me the 5-number summary along with the mean. The mean high in Calgary is 10 degrees, so that's kind of nice. Not too warm, not too cold, I guess. And the max at this point was 36.1, although we beat that a few years ago, which is good as far as I'm concerned. So what I want to do is convert this data from Celsius to Fahrenheit, which I claim here is less depressing because, yeah, 36 is not that exciting of a temperature. What does it look like if we convert it into Fahrenheit? And the way we're doing it is pretty straightforward. It's just this linear transformation. So this is the slope of our linear equation, 1.8 or 9/5. Multiply all the highs by that, and you can do that straightforwardly. Like if I take a look at Calgary highs, it's just a bunch of numbers, right? Over 46,000 numbers over the years for the different days in Calgary's history. But all I'm doing is multiplying every single one of those numbers by 1.8, and then I add 32 to the result of that, or the product, I guess you would say. And that gives me the highs in Fahrenheit. So the whole thing looks like this. And again, I've got over 46,000 numbers in here. But they're numbers that an American would appreciate, like 80 and 74, so on and so forth, not like 30 or 25. Yeah, so for whatever that's worth, we can also look at the overall summary of that information. And the maximum high here is about 97 rather than whatever it was, 36 for the previous set of data. Now what I want to do is plot the Fahrenheit and Celsius data alongside each other just so you get a sense of what this looks like. And we're going to use this command that I mentioned in the last video, this PAR command that kind of sets up a row and column structure for plotting graphs alongside each other in R. We're going to use this command here, which gives us 2 columns and only 1 row. So when I do that, it'll set up the window, just as a blank window. I got to put something in it. And so what I want to do is just plot the histograms of the 2 basically different units of measure of the data alongside of each other. So one for Fahrenheit and one for Celsius. We'll start with Celsius, and I don't have the command here up on the actual web page, and I should probably put it there so you know exactly what I'm doing, or at least you can watch the video if you want to get a record of it. So one of the reasons why is when I originally taught this course, I was just having people walk through these sort of command sets in class, but we kind of ran out of time when we did that, so I normally just do it myself. But either way, let's do it together by watching this video and say let's plot the Calgary highs, and we can do it that way. Actually, that's not what I wanted to do. There's a command called plot in R. It gives you a lot of data. I want to simplify that data a bit, so let me go back. I should have written the commands down on that web page because I forgot them. Okay, we're going to set up our little plot structure that way again. We're going to not plot a plot. We're going to plot a histogram in Celsius, and it'll look like that. So we can see what the distribution looks like. And it's not exactly normal, but it's kind of got that bell curve shape. And what I want to do is kind of compare it to what the Fahrenheit distribution would look like. So I can plot that next to it over to the right. Maybe expand these a little bit so we can see what's going on the x-axis a little bit better. Yeah, and then they both have the same general distribution shape, right? So they're skewed a little bit here to the left, kind of has that bell curved shape, if you want to say it. Maybe it looks like the letter J to you, I don't know. But you may notice there are some fine-grained differences between the two distributions. So I said if you use a linear transformation to convert data from one unit of measurement to the other, it shouldn't change the shape of the distribution. And that's basically true, but what we're seeing here is a different sort of histogram shape because we're using kind of different widths of the columns between the two units of measure, basically. So in some cases, you might get a higher column, in some you might get a lower column, just based on like how you're splitting things up. So if you wanted to, I'm not going to go through the trouble of doing this, but if you wanted to say make sure the breaks are on the exact same spots, just using the conversion from Celsius to Fahrenheit for these two distributions, you should wind up with the exact same histogram shape. But otherwise, you might just keep this in mind. The point is not to show you that it winds up being exactly the same, but that it can change in sort of superficial ways that might be misleading. So don't forget this. If you do wind up converting your units of measurement, they might show superficial differences based simply on that conversion, even though it's essentially the same distribution shape underneath or underlyingly. Yeah, I'm not going to say anything further about that, but I will show you one other example, which is kind of interesting to me, or hopefully will be educational too. So for this, I'm going to load up some data that I'm calling the point light response data. And we'll put it into a data frame called PLD data. Okay, so this is based on a study that I did a long time ago as part of a research lab when I was a postdoc. It was kind of the first project they had me do. Just said, well, we got this project running. Can you help out with it and like make something of it? And it was kind of interesting the way it worked. I didn't have anything to do with the generation of the stimuli, but they're quite interesting to look at. So this is a lab that was interested in audiovisual speech perception, like how much information can you get out of the visual domain when you're trying to understand what somebody is saying. So they had both what they called full face and point light displays video of speech of different speakers just saying one word at a time. And I'll show you the full face displays. If you've taken my phonetics classes, you've seen these before, or a few of them at least. I'm going to make sure the sound is muted on my computer. And unfortunately, my QuickTime player died. I have to play these through the VLC media player, which is not as user-friendly. But we'll take a look at these. So, okay. So the problem with these this player is that it shows the name of the file at the bottom of the screen, which is not anything we need. Anyways, this is a full face video, and the shtick here is that I will play you the video, and then you should guess what this person is saying. And I'm giving you a speaker who tends to be very clear in terms of how she like articulates when she speaks, so it's usually fairly easy to figure out what she's saying, even though you can't hear anything. And some people might be better at it than others, but you should be able to get some information out of what she's saying here. Oops, see, like I told you, it doesn't work very well. Try that again. Nope. I might actually have to find a different way to play these because it's not doing what I want it to do. Okay. Yeah, I'm going to pause the video and restart it. All right, apologies for that interlude. I've gotten a new media player on my Mac now, and we'll see if it works a little bit better than what I had before. And actually, I just closed it. I don't know if I can... Yeah, this one did not work so well. I wouldn't recommend it, even though the internet does. This one seemed to be working better. at least for our purposes for tonight. So I'm going to try to play some of these full face videos for you. So again, this is a speaker saying one word at a time, and you just watch her face, and you should be able to get some information out of this. And usually when I drop it on here, it kind of plays automatically. So I'll try to stop it before it does that. Yeah, okay, good. That seemed to work. So we'll wait for this little taskbar to go away down at the bottom, and we'll watch this single video. You can maybe tell me what you think she's saying. Okay, that one's not easy. I'll play it again. Yeah, so this one is, if I turn up the volume all the way, is the word
king.
King. Okay, that one's tricky. We'll try the other two just for kicks, and see if we can get anything out of those. Like I said, people often, well, and actually say it, but sorry, that went by pretty quickly. And that wasn't intended either. But people often think they cannot read lips very well, but maybe these last two convince you that maybe you have more talent in that domain than you thought. Yeah, so what is that? Yeah, we'll listen to it with the sound on, and maybe it'll correspond to what you're thinking.
Rat.
Rat. Okay. Let's try one more. Full face number 3 here. Yeah, and that went by before I wanted to play it, but here we go again. Maybe that one's a little bit easier. We'll do it one more time. Okay, what does she say?
Rough.
Rough. Okay, that one I could get, but I've seen these a lot over the years, so I don't count. Either way, you should be able to feel like you're getting maybe some information, maybe you got close on some of the sounds, maybe you got the whole word when you can see a full face like this. So like I said, I was brought into this project and they said, well, we already have this other set of videos where we are not showing people the entire face of the speaker, but instead what we've done is put glow-in-the-dark dots over their faces and some of their articulators too, and then film them under a dark light. So that you can see these dots moving around, sort of in the shape of a face. And we wanted to know, could people get any sort of visual information out of that? So I ran this experiment where I had people watching these videos over and over again, and then trying to figure out what word are they saying in these videos. I'll play a few of them for you. Yeah, you can let me know how you do in the comments, I guess. Oops, why does that keep happening? So here's what they look like. Stop. And we didn't really see it well the first time, so I'll play it for you again a couple times. So you can see there are these dots they put on the speakers' faces. This one's the tip of the nose. These are the cheeks. You can kind of see the outline of the jaw maybe. And then down here we've got like the lips, and there's some dots on the teeth as well. I think they put one on the tongue too. Yeah, I don't know if it was the optimal sort of dot layout or not, but here we go. This is what it looks like. And maybe you figured out by now that I'm going to play the same words we saw before.
King.
Right. I don't know if it's the exact same speaker or not, but we'll take a look at the other two and see how easy it is to interpret those in light of this new information. Yeah, so here's number 2. And maybe you can remember this one.
Rat.
Is rat. And then the last one is the word
Rough.
rough. Okay, so yeah, with rough or rat, more so than king, you're getting some information with the lips, at least in the full face displays, right? So ra, you usually round your lips a bit for an for uff, the f at the end of rough, you curl your lower lip underneath your upper teeth, make a f sound. So there's some information there you might be able to get.
Rough.
I can't really see much contact here between the teeth and the lips, but
Rough.
You can maybe guess without the audio that something like that might be going on. I don't know. It's hard to tell. Your mind has to fill in a lot of the gaps, right? So anyways, what I did in this experiment was play these videos to observers basically, or participants, over and over again, and then to try to help them figure out what was going on in these point light videos. After they would see a video, we'd show them like what the word was, or play. We actually used a variety of different kinds of feedback. We either like show them the word, or we play the video with like the word on the screen, or they just hear the word, so on and so forth. And then we basically found the general pattern was that if you repeat it to them, then over multiple repetitions, they get better at identifying the words, or at least parts of the words. And then some feedback turns out to be more better than others, more better than others. So if like audio visual feedback was better than just like seeing the word, right? Because the word written out as a word, because you're seeing the actual event again and understanding it in terms of what is being said, rather than getting abstract representation. I'm getting far afield here. This is kind of besides the point for this video, but the point I want to emphasize about these point light videos is they're hard. It's not easy to get information out of them, and hopefully you got that experience, even though I kind of showed you what the answers were before I showed you the videos themselves. So yeah, and it turns out people did really, really poorly in terms of like identifying the percentage of the numbers of words they did really, really poorly when we measured their performance in terms of the percentage of words they identified correctly in these. And with that percentage would get better if they got a lot of feedback on particular words. But at the start, they were just really, really poor. They hardly got anything. And in fact, there were some people who were like in a no feedback condition, and they were just like starting to type random things into the response box for each video because they couldn't figure out what was going on, including some choice comments that I still remember to this day, even though I ran this experiment like 17 years ago. Yeah, sometimes participants can just lose interest, right? So you don't want to design an experiment like that because you wind up getting like really bad information out of them, and it's just a waste of everybody's time. But be that as it may, this is the way we ran it. And I think I've still got my data frame open here. Yeah, so there are two ways we measured how well they did. And you can see here we ran full face videos, point light videos, and then this is the differing number of like repetitions of feedback that they got. So there's like I should mention as well, there's like a pre-test and a post-test where they got no feedback, and I just used that as a baseline to measure with like how they were improving over time in the feedback conditions. And then some people got the same video, or in some cases the same video would be repeated like twice. Sometimes it would be repeated 4 times, sometimes it would be 8 times, so on and so forth. And then we measured how many phonemes did they get correct, how many words did they get correct. And I'll just show you, as long as we're here, as this says, number one, how to make a scatter plot of this data, and then number two, get a sense of like how poorly the subjects were doing. So this is the best sort of measure of like, basically, this is where we'll see the best scores for this set of participants. This is looking at the words for which they saw the video 8 times, the point light video 8 different times, getting feedback after each repetition. And then we're measuring how well they did in terms of the phonemes correct. So like if they saw the word rat, if they said, rap instead of rat, then they got 2 of the phonemes right? Anyways, this is just the syntax you need to use in R to kind of get that specific subset of data. We'll dump it all into this vector here called PL8 phonemes. What I'm going to do is actually it's a data frame, not a vector. I'm going to create a vector of x values from 1 to 20, like that. And then I'm going to plot those x values on the x-axis, because we had 20 participants in each of the conditions here. So when I use the plot command, as maybe you can see, there's probably tiny font in the video, but what goes in the first part of the parentheses is what's on your x-axis. So this is the x values. And then what goes on the y is whatever you specify here. So I want to plot the percentage of phonemes they got correct in this particular condition with 8 repetitions of the stimuli. And then this last bit here, comma, and then put P in quotes, is that the P means I just want points. So I'm going to just plot open circles at each sort of percentage value that every single participant got. Yeah, so I'll plot that, and it should show up in my plotting window here. Actually, I'm going to restart that. It's not terrible, but I want to do that not in sort of just half of this window, but the whole thing. And so this is should give you a sense to how well they were doing. So this is percentage, but it's basically going from 10% on the bottom end to 80% on the high end. So there's one person who got about 80% phonemes correct, which is great. One person got 10% correct, and the rest are in the middle, maybe centered around 50% or so correct. So about half of these phonemes they could get with many, many repetitions over time. But the way I'm plotting it here, it just kind of random. So this is just, we assign each subject a number as they went through the experiment. So 1, 2, 3, 4, 5, all the way up. And there's kind of no rhyme or reason to how we're plotting the data here. So I'm going to change that a bit by sorting the Y values, the percentages correct, in ascending order. So I'm going to use the sort command to do this. So instead of just plotting this by itself as it is in the Y, on the Y-axis, I'm going to sort that information by putting those percentages in the sort command. And then this will make it look a little bit cleaner for me by just putting them in ascending order like this, from about 10% correct to a little bit over 80% correct. And now we can see that this subject is a pretty good outlier here, doing really well. Most people are somewhere in the middle, and we're getting a couple stragglers here down at the low end. Yeah, so this is easy to do, and this is, a scatter plot that's organized, but that's how you make a scatter plot in R. And what I want to use this data for is that it's just to emphasize that this is a case where people did really poorly because it's a very difficult task. So you get a number of people who are kind of at the very low end of the scale of percent correct, such that you could get what are called floor effects. Oftentimes in perception experiments, we talk about ceiling effects, where the task is so easy that they kind of run up against the 100% mark, and there's not much sort of differentiation between how well the different subjects are doing. They're all doing basically 100% correct, and you're not really getting information out of your experiment that way, because if you know that people can just do it perfectly all the time, like, you don't know why they would ever screw up. So here's a case where it's the opposite of that, where it's so hard that some people just never get it right. So you're not really getting much information out of them either. And one way to kind of stretch the scale on the y-axis is to use what's called an arcsine transformation. Now, I'll mention that when I was kind of going through the graduate education system back in the 90s, this was fairly commonly used device when you had data that kind of was on a scale from 0 to 1, or like 0% to 100%, to try to sort of get it from clumping up on those extremes and make it sort of more linear, like what we see here in the middle of the scale. You could use this arcsine transformation before you sort of apply different tests, specifically usually in ANOVA, to the data. That's getting a bit ahead of where we are now in the class, but I'll say that used to be a common thing for people to do. Now it's recommended that you not do it, but just to see what the effects of this transformation are, I'll show it to you in this particular video, and then say probably don't use it at this point in time. When you read older papers, you might see other people have used it, but just try to avoid it for now. And what we're going to do is use this formula to take our percent correct information here, and we're going to spit it through this somewhat complicated formula that I'm not going to dwell on the details of, because, like I said, I don't want you to actually do this. And then we're just going to spit the results of that into this vector called transformed. And I've had people ask me in the past if it makes any difference whether I use an equal sign here or this sort of assignment operator, like the arrow pointing at transformed, and the answer is I don't actually know. I don't think it makes a difference, and it doesn't look like it does, so you can use either one in this particular case, just so you know. But what I want to do here is that instead of plotting just the raw percentages correct, I'm going to plot those transformed percentages correct, and this will be subtle. Maybe I'll load this up so you can see it change a little bit before I hit return on this command without wasting too much time, hopefully. So yeah, boom. Okay, so yeah, it tweaked the middle to kind of be more condensed, and then it's stretching things out on the extremes a little bit, so that you aren't running up against sort of the limits quite as easily. Maybe I'll go back and forth with those two. So we'll do this. And we can see it kind of goes from 0.1 to 0.8 on the extremes. And we go back to the transform data. And we're not sort of running up against the edges as well. So we're more from like 20% to 70% instead. Yeah, so it's harder to get out to the limits. It's harder to get those floor effects or ceiling effects when you do this sort of transformation. Yeah, and this is basically, well, we're doing a square root here, so that's not really a linear transformation, but otherwise we're doing some division and multiplication here. Again, I'm not going to get into it that much, but just to show you maybe a little more clearly the effects of this transformation, I'm going to use these three commands. Again, sort of setting up the plotting structure with the first one, and then just plotting the two next to each other in two different columns. And you can see how they look different from each other. So this is the original over here, and this is the transformed one over here. And like I said, it's just harder to get out to the extremes in the arcsine transformed data than it is in the original. So that kind of helps prevent those problems from arising. That's the idea at any rate. Yeah, and I can also show you what this looks like in a condition where the subjects did even worse in the experiment. So this is still looking at the phonemes data, and they're only getting one look at this set of videos, so they don't get the feedback on it. So they're just kind of really guessing in the dark, both figuratively and literally. And so for this, I'm just going to do the same sort of transformations and then plot them in the same way, side by side. And you'll see that overall percentages will go down to here. And we're still getting the same effect, though, that it's kind of pulling the data away from the lower limit of 0%. So this one poor person just did, I don't know, maybe 3-4% correct for phonemes for this entire set of videos, which is really grind. There's a reason maybe why they were saying mean things in the responses by the end of the experiment. But if you look at it in arcsine transformation land, then it's not quite so bad, but it's still worse than everybody else. So you're kind of preserving the same overall structure of the data, not exactly, and in particular, not on the edges of the scale. But that's what the arcsine transformation does, and that's one case where it might come in handy is if you have an extremely difficult experiment or maybe even an extremely easy one. In both cases, what you're probably better off doing rather than using that transformation is designing your experiment better so it's not hitting those limits, because that's going to cause you fundamental problems when you're analyzing your data. All right, I've talked way longer for this than I wanted to, so I'm just going to stop it now, and then next time we'll talk about various issues in sampling, which is kind of at the core of what we do as experimental scientists. So I will see you guys then.